In today's video, we look at antiderivatives. Right, the goal is we want to find an easier way of evaluating a Riemann integral that was studied in the previous video. We do this by looking at the antiderivative. And really, all an antiderivative is it's the opposite of a derivative. So in this video, we're going to look at what an antiderivative is, as well as some of the basic antiderivatives. We'll also look at what's known as an initial value problem. Now, an antiderivative, we say that a function, capital F, is an antiderivative of the function little f if big f prime of x is equal to little f of x for all x in the domain of little f. So, for example, notice that the derivative of x squared is equal to 2x. So what this means is x squared is an antiderivative of 2x. Also, however, notice that the derivative of x squared plus some constant c also equals 2x. So what this is saying is that x squared plus c is also an antiderivative. So this observation leads to this theorem. We let f be an antiderivative of little f, over an interval I. Then we have two statements. First, for each constant c, the function given by big F of x plus c is also an antiderivative of little f over the same interval. The second statement, if big G is an antiderivative of little f over the interval I, then G differs from f by a constant. Right, so what this statement says is that the antiderivative of a function is unique up to a constant. Now, we shall prove this. I'm only going to prove the first statement. The second statement is actually a consequence of the first. Right, so suppose that f is an antiderivative of little f over an interval I. Right, by definition, that means that big F prime of x is equal to little f of x. Let g of x equal big F of x plus c for some constant c. Right, so all we're going to do is add a constant to this antiderivative. Then look, g prime of x is the derivative of big F of x plus c. Right, this is the derivative of big F of x plus the derivative of c. Right, derivative of big F of x is f prime. Derivative of c is 0, but f prime of x has to equal little f of x. So g prime of x is equal to little f, and therefore g of x is an antiderivative of little f of x. That is what we wanted, and so the proof is complete. Notation. We represent the antiderivative this way. This is known as an indefinite integral. Right, and this will sometimes be read as the integral of f of x dx. Right, so it could be read as the antiderivative of f of x or the integral of f of x dx. We will now look at some basic antiderivatives based on the derivatives that we have previously studied. Right. So first, notice that the derivative of k times x was equal to k. Right. Well, that means that the antiderivative of k dx is equal to kx. And remember, there's always a constant of integration attached. Right, plus any arbitrary constant. Next, recall the power rule. That said the derivative of x to the n was nx to the n plus 1. Right, this would mean that if we take a look at the antiderivative of x to the n, this would be x to the n plus 1 divided by n plus 1. This is known as the power rule for integration. Now, derivative of natural log absolute value of x. This is going to require a little bit of work. So if we look at the natural log of the absolute value of x, right, this will be the natural log of x as long as x is greater than 0. It'll be the natural log of negative x if x is less than 0. Right, remember, x cannot actually equal 0. If we now take a look at this derivative, it is also a piecewise function. It'll be 1 over x if x is larger than 0. It'll be negative 1 over negative x if x is less than 0. But negative 1 over negative x is still just 1 over x. So this derivative here is 1 over x, which means that the antiderivative of 1 over x dx is the natural log of the absolute value of x plus a constant. Next, recall that the derivative of e to the x was e to the x. This means that the antiderivative of e to the x is e to the x. Right? So we have these four so far. Let's now look at the trigonometric functions. So we had derivative of sine of x was cosine, which means the antiderivative of cosine is equal to sine. We had the derivative of cosine was negative sine. That would mean that the antiderivative of sine is negative cosine. Derivative of tangent was secant squared. Means the antiderivative of secant squared is tangent. Derivative of cosecant was negative cosecant cotangent. Means the antiderivative of cosecant cotangent is negative cosecant. The derivative of secant was secant times tangent. So the antiderivative of secant times tangent is secant. And finally, the derivative, don't know why I wrote t, of cotangent is negative cosecant squared. So the antiderivative of cosecant squared is negative cotangent. Finding antiderivatives of secant, tangent, cosecant, and cotangent requires a little bit more study. While we could theoretically do it in a Calc 1 course, these are not typically studied until Calculus 2. We have three more to look at. Recall that the derivative of the inverse sine was 1 over the square root of 1 minus x squared. This would mean that the antiderivative of 1 over the square root of 1 minus x squared is the inverse sine. The derivative of the inverse tangent is 1 over x squared plus 1. So the antiderivative of 1 over x squared plus 1 is the inverse tangent. And the derivative of the inverse secant of absolute value of x. Again, this is going to require a little bit of analysis. Right, so the inverse secant absolute value of x is the inverse secant of x whenever x is greater than or equal to 0. And it is the inverse secant of negative x whenever x is less than 0. So if we take its derivative, we would wind up with 1 over x times the square root of x squared minus 1, as long as x is greater than or equal to 0, negative 1 over negative x square root of x squared minus 1 when x is less than 0. In both cases, we get 1 over x square root of x squared minus 1, meaning the antiderivative of 1 over x times the square root of x squared minus 1 is equal to the inverse secant of absolute value of x plus a constant. There are two basic rules for antiderivatives. And these two rules are fairly obvious. So first, we're going to say let k be a real number. Right, we have what's known as the constant multiple rule. Which says that the antiderivative of k times f of x is k times the antiderivative of f of x. And then we have the sum and difference rule, which says the antiderivative of f of x plus or minus g of x is the antiderivative of f of x plus or minus the antiderivative of g of x. These follow directly from their corresponding differentiation rules, the constant multiple rule for derivatives, as well as the sum difference rule for derivatives. Let's now take a look at some examples of antiderivatives. First, let's evaluate the antiderivative of 5x cubed minus 7x squared plus 3x plus 4. Well, the first thing is let's use the sum difference rule. Write this as the antiderivative of 5x cubed minus the antiderivative of 7x squared plus the antiderivative of 3x plus the antiderivative of 4. Then for the first three, we can use the constant multiple rule. 5 times the antiderivative of x cubed minus 7 times the antiderivative of x squared plus 3 times the antiderivative of x, then plus the antiderivative of 4. Once again, looking at these first three, each one is a power rule. So it'll be 5 times, power rule says, add 1 to the exponent, so x to the 3 plus 1, then divide by that. Same thing, x to the 2 plus 1 divided by 2 plus 1, x to the 1 plus 1 over 1 plus 1, and then that last one is a constant, and that's just 4x. And at the very end, just add an arbitrary constant. Now if we simplify this, we'll have 5 over 4 x to the 4th minus 7 over 3 x cubed plus 3 over 2 x squared plus 4x plus our arbitrary constant. And this would be our antiderivative. Next, let's take a look at the antiderivative of x squared plus 4 times the cube root of x all over x. First, let's write the cube root of x as a power. So this is the antiderivative of x squared plus 4x to the 1/3 all over x. Now we do not have a rule for this. However, notice that the denominator is a monomial, meaning we can take each term in the numerator and divide it by the denominator. That'll leave us with the antiderivative of x squared over x, which is x to the first power, plus 4 times x to the 1/3 over x, that's 1/3 minus 1, so x to the negative 2/3 power. Now we can use the sum difference rule as well as the constant multiple rule. This is the antiderivative of x plus 4 times the antiderivative of x to the negative 2/3. Each of these is a power rule. X to the 1 plus 1 over 1 plus 1 plus 4 times x to the minus 2/3 plus 1 over negative 2/3 plus 1. And don't forget the arbitrary constant at the end. We'll have x squared over 2 for the first term. X to the 1/3 power divided by 1/3. Right? Fully simplifying, this is now x squared over 2 plus 12. Let's rewrite it as a cube root. 12 cube root of x plus a constant. Now let's go ahead and evaluate the antiderivative of 4 over 1 plus x squared. Well, if we rewrite this, factor out the 4 using the constant multiple rule. Antiderivative 1 over, let's write that as x squared plus 1. Now that matches the form of an inverse tangent. So our antiderivative is 4 times the inverse tangent of x plus a constant. And finally, let's go ahead and take a look at the antiderivative. Tangent of x times cosine of x dx. Now again, we don't have a rule for this. However, let's write tangent as sine over cosine. Now notice that the cosines are going to drop out. This is actually just the antiderivative of sine of x. And that is negative cosine of x plus a constant. We now turn our focus to a type of problem known as an initial value problem. Now normally, it would be impossible to solve for the constant of integration. However, if we know the value of f at some point, let's say we know that f of x naught is equal to y naught, then we can solve for this. We can solve for the constant. Now this is known as an initial condition. And the initial value problem is dy dx equals f of x given f of x naught equals y naught. This is the initial value problem. So really what an initial value problem is finding a specific antiderivative given some initially known value of the function. As an example to an initial value problem, let's go ahead and take a look here. A car is traveling at the rate of 88 feet per second when the brakes are applied. The car begins decelerating at a constant rate of 15 feet per second. We want to determine how many seconds elapse before the car stops, and then how and then determine how far the car traveled during that time. Right. Car is traveling at the rate of 88 feet per second when brakes are applied, and there's a constant deceleration of 15 feet per second. What that means is that our acceleration A of t is negative 15 feet per second per second. But acceleration is change in velocity. So dv dt is actually equal to negative 15 feet per second per second. And we also know that initially the car is traveling at 88 feet per second. We have an initial value problem. This is the initial value problem. Right, we want to determine how many seconds elapse before the car stops, so we want to solve for v of t first. So v of t will be the antiderivative of negative 15 dt, which is negative 15t plus a constant. We use now the initial value to solve for that constant. We know that v of 0 will be, according to this, c, but that has to equal 88 feet per second. So our function, our velocity function, is 88 minus 15t. We now use this to solve the first question, which is how far or how many seconds elapse before the car stops. So we want to solve v of t equal to 0. This means that 15t is equal to 88. So t is 88 over 15, and that is about 5.87 seconds. So it takes just about 6 seconds for the car to stop. Now, how far does it travel, which means we want a position function? Well, we know that v of t is the change in position, ds dt. So ds dt will equal that 88 minus 15t, and since we want to know how far the car is traveling, we can set the position of when the car begins to decelerate at 0 feet. So once again, we have an initial value problem. S of t will be the antiderivative. 88 minus 15t, which is 88t, minus 15 t to the 1 plus 1 over 1 plus 1 plus a constant. So 88t minus 15 halves t squared. Using our initial condition, s of 0, if we plug it into what we just found, we just get c, and that has to be 0. So we can take our position function to simply be 88t minus 15 halves t squared. How far does it travel? Well, let's plug in 88 over 15. 88 times 88 over 15 minus 15 halves times 88 over 15 squared. Plugging this into a calculator, you'll find this gives you 3872 over 15 feet, which is about 258.13 feet. So it goes about 258 feet during this time of deceleration. One of the most common applications of initial value problems occurs in physics in the study of free fall motion. So consider an object that is tossed vertically in the air from an initial height of y naught. Right, so we'll just call this height y naught with an initial velocity of v naught. If we ignore air resistance, then the object is only under the influence of gravity. Since it's only under the influence of gravity, that means A of t is a constant negative g, where g is the acceleration due to gravity, and that is 9.8 meters per second, or about 32 feet per second. An object under this condition is said to be in free fall, and the motion is known as free fall motion. So the idea is we want to find a model for free fall motion. Well, solving it is equivalent to solving this. First, find A of t, which remember is dv dt, given, or equals negative g, given that v of 0 is v naught. Okay. Actually, let me rewrite this. It's actually equivalent to solving this. The second derivative of s with respect to t is negative g, given v of 0 is v naught and y of 0 is y naught. This is still an initial value problem. It's just a second order initial value problem. The first thing we want to solve is for v. So v is going to be the antiderivative of negative g, which is negative gt plus some constant, call it c1. Now we know that v of 0 has to be v naught, but that is negative g times 0 plus c1. So c1 is equal to v naught, and so our velocity is v naught minus gt. Now we can solve y of t is dv dt. I'm sorry, v of t is dy dt. So y is the antiderivative, v naught minus gt dt. That is v naught t minus gt squared all over 2 plus a second arbitrary constant, call it c2. Now we know y of 0, based on this, plug in 0 is just c2, but that has to be y naught. So our free fall motion is given by the equation y of t is y naught plus v naught t minus gt squared all over 2. This is a model for free fall motion. And again, remember that means that the object in question is only under the influence of gravity. This is ignoring any kind of air resistance. And that concludes our study of the antiderivative. The next video in this series will then introduce a technique of finding antiderivatives known as change of variable. So I will see you all in the next one.